Okay, so the main thing, what you're looking for is it a metal and a non-metal? Those are your ionics, or is it all non-metals? So back to the periodic table. Let me erase this stuff from the previous class. Okay, so metals are over here, non-metals are over here. Okay, so one from each side, that's ionic bonding. When we talk about, the next question says something about like what's the difference in how they bond. So ionic bonding, if you remember, we talk about it as electron transfer. So the metal is actually going to lose an electron and give it to the nonmetal. Okay, so you're going to get a positively charged ion from the metal. So, sodium plus, right? Or iron 3 plus, I think it was. And then it's going to bond with a nonmetal that took those electrons. So the bromines, those took the electrons with the iron. And you get FeBr3, okay? So that's the type of bonding when we talk about ionics. When we're talking about covalence, we're just talking about nonmetals. So I think the example in there, now H is a nonmetal, don't forget that, but CHCl3, okay? So no more are we transferring electrons, we're actually sharing the electrons. So this happens by electrons from each of them being attracted to both nuclei, and that's what we mean by sharing, is instead of an electron moving from one to the other, those electrons that are next to each other get attracted to the nuclei of both atoms. So what we need to do now at this point, this is still kind of background information that we knew before. What we need to do now is start representing those molecules something other than just the formula. Like up until this point, we have only really represented them as chemical formulas. Okay, so let's go back to that. So this is fine for a lot of things, but like look at CHCl3. Like, what does that really look like? Does that mean the carbon's bonded to the hydrogen, which is bonded to 3 chlorines? And are those chlorines like bonded to each other? Like there's no information there that's helping us, unexperienced learners yet to know what that actually looks like. So that's where we're headed in this chapter, is how can we describe their structure and how do we know what they look like? Because this molecule actually looks like this. The carbon's in the middle, the hydrogen's on one side, and then the 3 chlorines are spaced around it, okay? But how did we know that? How did we get to that point? And how do we know that those are single bonds? Like, why isn't that a double bond? How do we know when we're going to write a double bond in, okay? So that's where we're headed. To do that, we're going to use this method called the Lewis dot symbols. And I just realized I didn't talk about structure yet, so let me talk about that first. But we're going to get to these Lewis dot symbols. And we're going to do one page about ionic bonding because it is very straightforward, ionic bonding. It's like you can only have NaCl, right? You can only have one of each. You can't have Na2Cl or NaCl2. So it's very easy to represent those. The covalent ones are very complicated. So the rest of the chapter will be spent on covalent, okay? Just as a recap or a reminder, remember that when we have the electron transfer happening versus the electron sharing, oh, that is big. So electron sharing, electron transfer, it actually changes the structure of the chemical itself, okay? So in ionic bonding, when we say NaCl, we do not mean an individual Na and Cl. We mean a big mass of them. They're just in the ratio of 1 to 1, okay? So it's a big crystal. It's got maybe thousands, hundreds, millions, whatever, of NAs, and then the same number of Cls. And then they're all held together between the positive and negative attracting. So the sodium lost 1 electron to the chlorine. It gained the 1 electron. And now they're positive and negative, and they stick together. Okay, that's ionic bonding. And we have lots and lots of them stuck together. So ionic bonds are pretty strong. So and when we look at their melting points, the melting points are pretty high. These are like, thousands of degrees Celsius, right? Whereas water melts at 0 degrees Celsius, right? Very low boiling point, or moderately low at least. So why is that? Does that mean covalent bonds are like weaker than ionic? No. When something covalent bonds, it forms a molecule. It forms its own little unit. There's no individual unit over here of NaCl. But in water, there is an individual unit that actually has 2 hydrogens and 1 oxygen. It's not a ratio anymore. It is describing a particular unit or molecule. Now, when we talk about melting, we're not breaking the covalent bond between the hydrogen and the oxygen. We're actually breaking an interaction between molecules. So we'll get into that. I think it's like at the end of chapter, or at the end of unit 2, so like midway through the semester. We'll talk about those interactions. They're called intermolecular forces, but that's what we're breaking here, is like if we have some interaction between 2 molecules, that's what we're breaking. And that's why they appear to have weaker bonds. It's just that we're not breaking the covalent bond, okay? So an ionic bond and a covalent bond are similar in strength, but they form a very different structure in the actual solid or, these examples are solid, ice and salt, okay? All right, so moving along to the Lewis dot symbols. So if you look at your periodic table, this is the second row of elements. We're just talking about the main group elements. We're skipping over the transition metals. Everything I talk about today will just be the main group elements. So we're just going to completely ignore these guys for now. And when I say column 3, even if I'm not ignoring transition metals, if I say column 3, I'm talking about 3A. Okay, I'm talking about the main group elements. So as I'm talking about this, column 1, 2, 3, etc., those are the ones we're paying attention to. So in our notes, it says lithium, beryllium, boron, carbon. It's listing out the second row in order, okay? So when we want to represent those elements, we're going to write the symbol, and then we're going to write the valence electrons around the edges. So if you remember, we've got a bunch of core electrons. It depends on how many levels we've already gone through. But then we have the valence shell. And if we're talking about main group elements, that's 1 s orbital and 3 p orbitals. Okay, so valence electrons, which means that we have a total capacity for 8 electrons. This should sound familiar. So 2 in each of those orbitals, 4 orbitals, so 8 electrons possible in the valence shell. And if you look at neon, which is a noble gas, so it's completely filled its valence shell, it's got 8 dots around it, right? The way we represent this is thinking about each of the sides of the symbol as an orbital. So if you look at carbon, it's like we've got 4 different orbitals. It only has 1 electron each. We have not drawn it like this because we don't want to pair electrons up until they have to be paired up, right? We don't want to increase any electron repulsion. So just like when we drew the orbital diagrams, we're going to draw them separately until they need to pair up. If you're worried about this, we almost treat these 4 orbitals as equal in energy when we're drawing these symbols, okay? Because in reality, carbon actually looks like this. It's got 2 that are paired in the S, and then it has individual ones in the P, and one of them is completely empty. So if we were to describe this most accurately, it would actually look like this, okay? We don't draw it like that because these, we don't use them by themselves very often as atoms. We use them in molecules. We use them to describe when they're bonding. And once they start bonding, the S and the P's kind of don't look like S and P's anymore. They actually look more like 4 orbitals that are equal in energy. So don't let that bother you. If it wasn't bothering you, that's good. Just go with that. But if it was bothering you at all, just know that it's because they're going to form bonds, and that changes how the orbitals behave. And we'll get there and talk about it soon, about what they actually look like. Okay? All right. So when we go through across the row, we get 1, 2, 3 valence electrons, et cetera, et cetera. This should not be new. When we look at the periodic table, so I'm going to do this in blue, I'll write the valence electrons. We know that the first group has 1, the second group has 2, et cetera, okay? 3, 4, 5, 6, 7, 8. This is stuff you can't forget, okay? So if we want to draw the Lewis dot symbol of chlorine, it should have 7 dots around it. 2, 2, 2, and 1. If we want to draw phosphorus, it should have 5. Okay, so it should look like 1, 2, 3, 4, 5. That's how we do it. We go around in a circle. We pair them up when we need to. Okay? We have this idea of the octet rule. It's not really a rule, it's a guideline. But generally, things want to fill that valence shell. So when you see phosphorus like this, I want you also to kind of imagine that there's 3 open spaces where electrons could go into, right? This is actually why we see elements forming the charges that we do, because they're either trying to fill in their valence shell or get rid of the electrons in their valence shell. So that's kind of the second thing that's a reminder from before is the charge that they form, again, based on the column in the periodic table. So the first 3 groups are going to lose electrons so that they can have a empty valence shell, if you want to think of it that way. So the first group will lose 1 and become a +1 ion, because now it has 1 less electron than protons. Group 2 will become a +2. Group 3 will become a +3. 4, we don't really talk about. Some of the bottom ones will form ionic bonds, but carbon, silicon, germanium, those are not forming ionic bonds, okay? Those are only covalent, so we don't worry about their charge. When we get now to 5, now we're into the nonmetals. Those are starting to gain electrons, so those are filling in that valence shell. So phosphorus is in group 5. It has those 3 open spots, so it's going to gain 3 electrons. So it's going to be a -3. Oxygen and sulfur, they only have 2 open spots, so they will gain 2 electrons and become a -2. Halogens will become a -1, and noble gases generally don't do anything. They don't lose or gain electrons. Okay? So that's another important thing we need to keep in mind. All right. What I want you to do now is going back to these symbols. I want you to first, as a good reminder, write the abbreviated electron configuration for each of these. So abbreviated, meaning in this case, it would start with helium in brackets, and then you write it in its valence shell. And then I want you to write down the elements from the 3rd row following this same method. So like we did this for phosphorus already. We said phosphorus is going to look like this. Okay? So I want you to do that for all of the elements in the 3rd row. Okay, so 2 or 3 minutes on that. Abbreviated electron configuration and 3rd row that says Lewis dot diagrams. Last semester we had that room that was like perpetually cold. So at least I knew how to dress and knew that it would be cold all the time. It is so freaking hot down here. Okay, so in case you forgot what electron configurations are, that's where you're labeling electrons as the superscript for what orbitals they're in. So let me just write a couple more of these for the bottom ones. If you didn't get a chance to write all of them, that's okay. We're just going to talk about a couple. It's mostly like I want to make sure you're connecting all of these ideas of columns on the periodic table, what they look like when we draw them as symbols, where those electrons actually are in the orbitals. We need to connect all of those ideas together so that as we draw the symbols for molecules, we understand where those electrons are all coming from and where they physically are in the atom, like in the orbitals, okay? So first thing to notice about the symbols themselves, if they're in the same column, like nitrogen and phosphorus or oxygen and sulfur, they're going to have the same number of dots around them. It does matter if they're paired or individual. It does not matter what side they're on, okay? So like in phosphorus, I drew the 2 on the top, and here they're 2 on the side. That doesn't matter. It's not right or wrong. Magnesium, I drew them top and side, and this is side and side, okay? That doesn't matter. The number of them matters, and then where they are paired and not paired. So like for magnesium, this would not be correct. Don't pair them up until you have to, okay? So go around the circle, 1, 2, 3, 4, then start pairing them up, okay? All right, the other thing, remember, that's similar is in a column on the periodic table. So let's take boron and aluminum. You end up with a really similar electron configuration. It only differs by the principal energy level. So these guys, their valence shell is at n equals 2. These ones, their valence shell is at n equals 3. But both of these have 2 electrons in the s and 1 electron in the p, okay? That's what's going to cause them to have really similar chemical behavior. And now we're showing their symbols look the same too. Okay? So again, just connecting all of these different ideas as different ways of representing the elements. Okay, so now let's do this for ionic bonding. Let's show how we're going to represent ionic bonding. We just answered that. What similarities? I just answered that. So we talked about their electron configuration, the dots that are surrounding them. And we didn't highlight this specifically in here, but when we were on the periodic table, we talked about the charges that they'll form. Okay, from either group, so this could be the ones from group like a row 2 or row 3, pick a metal and a nonmetal, and then I want you to show me the symbol for what ion it's going to form. So like, for example, for the metal, you could do Na, but I want you to show me what it's going to look like after it's formed the ion that we know it does, Na+, okay? And then for the metal and whatever non-metal you pick, here, let's do this. I'm going to give you Na and Cl. I want you to do 2 different ones and make them not the same charge. So like pick one that's +1 and -2, or +2 and -3 or something, okay? So in this example, I would show how those 2 are interacting. Like what's happening with the electrons in Na and Cl to cause them to form Na+ and Cl- and form a bond. Okay, so take a shot at that for, I'll just give you one in particular. Let's do Na and O, okay? So draw me symbols for maybe do before they formed ions and then what they look like after they formed ions. I just want you to start on it, so I'm going to give you like a minute. Okay, so I'm going to start with the NaCl as our easy example, and then we'll do the NaO together as well. So when you get NaCl, those two elements near each other, what's going to happen is the electron from the sodium is going to actually move to the chlorine. Okay, so we now represent that by putting another dot over there. And the other thing that we do is we put brackets around it and put the charge. So anytime it's not neutral, the symbol needs to have brackets. So you still draw in the dots. There's 8 now. And then we put the charge. For the sodium, we're going to draw it like empty because it's lost all of that valence shell. Now, technically, that just means its new valence shell is the n equals 2, but we're just representing what it was and kind of where those electrons went. So there are no more electrons in the n equals 3, so we don't draw any dots, and we just show the charge, +1. And that's it. That's how we would represent a Lewis dot symbol, Lewis dot structure for an ionic compound. It's not very interesting. We just show the electron moving and then show they stick together because they're positives and negatives. The oxygen one is maybe a little bit more interesting because, as you'll notice, oxygen has 2 available spots, but sodium only has 1 electron. So what that's going to mean is that we need another sodium to provide another electron. This is not anything new. Back in chapter 3, we talked about how sodium will form a +1 ion, oxygen will form a -2, and because of that, the formula, we have to have 2 sodiums for every 1 oxygen so that it's 2 positives and 2 negatives. So the formula is Na2O. Okay? We're just showing now how those electrons move. So the electron from this sodium moves over here, and the electron from this sodium moves over here, and now we're left with Na+, Na+, and O, showing all 8 of those electrons, 2-. Now, the text says show, sometimes I wrote this, so I'm like, why does it say that? Well, I don't know, because I was not thinking clearly. Show how the 2 ions will interact to form an ionic bond. That's all you can show. They interact because the positives and the negatives stick together. Now, maybe it would look better if I wrote Na+, O2-, and then the Na+ on the other side. It doesn't matter, though. You're just showing that there's 2 of the positives and 1 of the 2 negative. Okay? Couple things to notice, and this is just to like hammer the point in. The octet rule, it is not really a rule, it's a guideline, because by the end of the chapter we're going to break it. But usually things are going to want to fill their valence shell, meaning have 8 valence electrons. Okay? The other way they do that, if they're a metal, is they lose all of those electrons so that now the next one down is the filled one. The only exception to that is hydrogen, because if you remember, hydrogen just has the 1s. That's its valence shell. There are no p's in n equals 1. So hydrogen does not need to fill in 8. It only needs to fill in 2. So this is what it looks like now. If we were to satisfy that valence shell or fill that valence shell, it would just need 1 more electron. Okay? So this is sometimes called the duet rule. So it doesn't need 8 total, it just needs 2. Everything else, though, needs 8. It either needs 8, like chlorine, or it needs to get rid of them, like sodium, so that now its lower energy shell has 8. And the same thing happens in covalent bonding. It's still trying to satisfy its octet, it's just doing it in a different way. Okay? So this is everything for ionics. Does anybody want to ask any questions about the symbols themselves or ionic bonding or how the electrons are moving before I move on? Because we're not going to talk about ionics anymore. Okay. All right. I want you to do these ones, you'll be able to do that pretty easily. And then at least take a minute and think about if you know the answer to that one, okay, for oxygen and sulfur. Okay. So symbols, you can just copy those, or hopefully you remembered how to do them. How many electrons? Well, first people are like, oh, 6, right? Well, it's not valence electrons. It's actually asking about electrons. So oxygen has 6, sulfur has 16, but who cares how many they actually have? They both have 6 valence electrons. We don't really care about the core electrons. Now, when you get into higher level chemistry, yeah, you're going to care that like sulfur's valence electron shell is further out. It's higher in energy. And so maybe that's going to make it a little bit more reactive. But for right now, all we really care about is how many valence electrons does it have and how many bonds is it going to form. And no matter what those core electrons are, it's the valence electrons and the number of them that we care about. So they both have 6. Okay? How many does it need to complete its octet? 2. Now, when we talked about ionic bonding, we said that means it needs to gain 2 from some metal. But the question on the bottom is talking about covalent bonds. Based on your answer above, predict how many covalent bonds we'll need to form. Guess what? It's the same thing. So in the ionic, it had to gain 2 electrons. In covalent, it's going to need to form 2 bonds. It's another way for it to get electrons. It's just that it doesn't completely take them from the metal. It's going to share them with nonmetals. So we'll show this in detail on the last slide. But before we do that, I want to switch back over to the periodic table, and we're going to add one more detail here, which is the number of bonds. Now, this is only really applicable, it is only applicable for the nonmetals, but the number of bonds is still going to correspond to how many more does it need to get to 8. So if we're talking about carbon, silicon, they have 4 valence electrons. They're going to need 4 bonds in order to get to 8, in order to fill that octet. Okay? For nitrogen's column, it has 5. It's going to need to form 3 bonds. Now let me show you what this looks like. So nitrogen, 1, 2, 3, 4, 5. That's what nitrogen looks like. So what's going to happen is that another element is going to come along and it's going to share, these two electrons are going to be attracted to both the nitrogen and the hydrogen. And when we do that, we get to basically count that bond that's going to have 2 electrons as part of it. We get to count them for both atoms. So by sharing them, it's like they both get to claim them to fill up their valence shell. Okay? So for nitrogen, it's going to form 3 bonds in each of those spots where it has an electron that's not paired up already. Okay? So it starts with 5, it needs to form 3 bonds in order to fill that up. With oxygen, it'll just form 2. Think of water, right? H2O. It's an oxygen with 2 hydrogens bound to it. The halogens just form 1. And again, the noble gases typically don't bond. I say typically because all of these bonds are usual, preferred. You talk to a biologist and they're going to be like, carbon always forms 4 bonds. Nitrogen and phosphorus always form 3 bonds. And then I'm like, oh, really? Phosphorus forms 3 bonds? What about phosphate, like ATP, ADP, right? Any of you biology students? You know that's what it looks like. It's got 5 bonds. Also, how can it have 5 bonds? Because that would mean it has 10 electrons in its valence shell. And oh no, we just exploded the octet rule. It's okay. It usually forms 3 bonds. Most of these things are not hard and fast rules, right? They are general guidelines to get us started. Okay, so think of the octet rule as a guideline. Think of these number of bonds as a guideline. It's a good place to start. Okay? And then I can rag on biologists too. All right, so let's do this for, we kind of already talked about this, so ignore that. Let's do this for hydrogen and sulfur. So last 5 minutes, I want you to show how hydrogen and sulfur would bond in order for both of them to get their valence shells filled up. Okay. So remember, hydrogen only needs 2. So it has 1 already, which means it just needs to form 1 bond. Never, ever, ever, ever have hydrogen look like anything except for that, okay? It will form a bond to something else. It will never have any electrons around it. It will never form two bonds. If you did it wrong, okay? What we mean when we say it forms a bond is that, yeah, there's some other element over here, but for hydrogen's sake, that element brought one electron with it, and hydrogen brought one electron. When we draw a line like that, we are talking about two electrons. It's a way to symbolize two electrons, but we draw it as a line to show that they're being shared between the two atoms. So the green one, I just want to do this in a generic form. Let's pretend it's like fluorine or something, okay? So it brings an electron, and then hydrogen gets its electron to be attracted to it and to be attracted to the other thing. Then the electron from the other thing still gets attracted to itself, and it gets attracted to the hydrogen. That's what we mean by sharing. Both electrons are being attracted to both nuclei. And when we look at hydrogen, we are going to say that hydrogen gets to count, because it's sharing with that electron, it gets to count both of those as part of its valence shell. Okay, so moving down to H2S, which is what the formula will actually be, I'm going to change these two electrons into a line to say that those are being shared. Same thing with the other two. I'm going to change those into a line. And then when I look at sulfur, I'm going to let sulfur use all of those electrons, including the ones from hydrogen, to say whether or not its valence shell is filled. So 1, 2, 3, 4, 5, 6, 7, 8. So that's how we say that sulfur has filled its valence shell. Hydrogen also gets to claim those. So when we're looking at does it fill the octet or the duet rule, we get to double count the bond. Okay? So the sulfur has its 8, the hydrogen has its 1, 2, and this hydrogen has its 1, 2. Okay? So that's the deal with sharing, is we get to double count the bond just when we're talking about does it satisfy the octet. Okay? All right. Likely video on Monday. Try to stick with it and pay attention, and then I'll see you guys next week.